All right, we made it. The last portion of our Chapter 8 lecture. Let's dive on in. So here's another part of the VSEPR model where we look at molecules or ions with lone pairs like the triiodide ion, okay? So we're going to look at this here, this shape where they've got all these lone pairs surrounding each of the ions, or each of the atoms, okay? The central iodine atom has 5 pairs around it. So it's broken that octet rule. But that means that it requires a trigonal bipyramidal arrangement. Okay, so several arrangements are shown here below, but which one will be the preferred structure, right? So we've got all of these different structures that are possible with 90-degree angles, 90-degree angles, or 120-degree angles. So here's where we're going to think about something, and you might even look at that 120-degree angle and say, that might make sense with those lone electron pairs wanting to repel each other as much as possible. So because of those electrons wanting to repel each other so greatly, that C portion, that will actually be what our triiodide ion will take the form of. And so it will actually be considered a linear molecule as well. So here we look at multiple bonds, okay? So we're considering the nitrate ion, which requires these 3 resonance structures, which we've looked at before. And remember, resonance structures are just different ways to represent the same molecule, okay? So they're all equivalent, but we need to represent the molecule with those double bonds in each of the nitrogen-oxygen bonds. While this is occurring, it looks as though this one's going to be shorter than these two because it's a double bond, but really they're all the same length. They just share those electrons, and this is the best way we represent it. So remember those resonance structures. So this is known to be a planar molecule with 120-degree bond angles, okay? So no one of those bonds has more electrons necessarily, so we don't actually see an increase of bond angles anywhere because remember, those resonance structures means that they're sharing those electrons between those 3 bonds evenly. This is just the only way we can represent it. So the planar is the expected structure for the 3 pairs of electrons around the central atom, which means that the double bonds are counted as one effective pair in the VSEPR model. So we're not looking at them as though there are more electrons in any of those bonds. So they're not truly given to a specific double bond. They spend their time around every oxygen atom. And this leads to the rule that multiple bonds are counted as one electron pair. Okay, so multiple bonds are still counted as one electron pair. So if we were to have any of those double bonds, we still only count them as one electron pair. Here's another rule for the VSEPR model that when a molecule exhibits resonance, any one of them could be used to predict the molecular structure. Whereas unlike lone electron pairs in molecules with bond angles of 109.5 or less, degrees or less, like water, the lone electron pairs in molecules of bond angles with 120 degrees don't require more space and change the bond angles of any other bonds. Okay? So how about those molecules that don't have one single central atom? So for example, the molecule methanol, or CH3OH, here's the Lewis structure, okay? We have carbon in the center surrounded by those hydrogens, but carbon is also bonded to oxygen, bonded to another hydrogen. And this is why, right here, this little OH, this is why we write it like this instead of CH4O. We write it as CH3OH, because now we can see that hydroxide on this end here. So the molecular structure could be predicted from the arrangement of pairs around the carbon and oxygen atoms. So there are 4 electron pairs around the carbon atom. So each of those bonds with hydrogen, and oxygen, those are all 4 electron pairs in total around the carbon atom, which requires a tetrahedral arrangement. But in this case, the tetrahedral will be slightly distorted by the space requirements of lone pairs. So the overall geometric arrangement looks like this. Okay, so we get mostly tetrahedral, but those lone pairs on oxygen make it a little bit bent So if we look at this, B is kind of the continuation of this right here. We've just left off those other hydrogens for a minute. So we get this slightly bent shape here between the carbon, oxygen, and hydrogen because of those lone oxygen pairs. Okay, so this is in total what that would look like. So you get that little bent downward shape here, and then the hydrogen comes up this way, and you know that you will have those electron lone pairs out here and out here, okay, affecting that shape. So here's a review of the VSEPR model. The rules to predict the molecular structure are as follows. We need to determine the Lewis structures based on the electrons. Then for molecules with resonance structures, we could use any one of those to predict the molecular structure. Just remember that even double bonds or triple bonds would be counted as a single pair. We don't act like those bonds have a greater negativity than anything else. And then you would sum the electron pairs around the central atom. In counting pairs, count each multiple bond as a single effective pair, just like I said. So double bonds, triple bonds, they're all a single pair. Then the arrangement of pairs is determined by minimizing electron pair repulsions. So if you have lone electrons, they will be very repelling. If you have an electron pair, so even if it's a single, double, or triple bond, they'll want to repel other single, double, or triple bonds just as much as any other. And those arrangements can be seen on table 8.6. And then lone pairs do require more space than bonding pairs do. Remember, because there's so much negativity in those lone pairs, and every bond, even if it's just hydrogen with one proton, it's still going to have enough positivity to not repel as strongly as lone pairs do. So you'll have to choose an arrangement that gives lone pairs as much room as possible and recognize that only the lone pairs may produce a slight distortion of the structure at angles less than 120 degrees. So that bent shape that we saw right here, it's only a slight distortion because of those lone pairs. Okay, it's not immensely great. All right. Now, how well does it work? Well, it works very well even up to molecules with hundreds of atoms. So when we get into, or if you get into organic chemistry where you have hundreds and hundreds of carbon chains surrounded by hydrogens, this VSEPR model still works well, but there are some exceptions. Okay, so phosphine, or PH3, is one example. So its Lewis structure is analogous to that of ammonia. It's very similar to NH3. It doesn't have the same molecular structure. Okay, so we've got NH3 on the right, PH3 on the left, but they are different. So like ammonia, we would assume that the bond angles are 107 degrees because that lone pair creates a little bit more, requires a little bit more space, but we actually observe through experimentation that the phosphine bond angles are actually at 94 degrees rather than 107 degrees, okay? So that's kind of interesting, and this could be explained, but requires many more rules to be added to the VSEPR model. So instead of explaining it, we kind of want to keep the VSEPR model as a general rule, not necessarily speaking to these anomalies. All right, there you have it. We're done with Chapter 8. Thanks for tuning in.